Okay, so last time when we ended, we were speaking about you have signals coming into devices, systems, and one of the things that we said is that it's all well and good when the system is when the signal is nice and continuous, which is what we would like to assume from things. And the example I had drawn on was that you have something like a process plant, and there's a measurement taking place to control something quite away from a control room, and the information has to be transmitted in some form or fashion. And somewhere along the way, the signal gets lost or broken for a little while. And then that creates what we call a discontinuous signal, which is basically in plain English, that the signal jumps from one value to the other and then continues along the way. That by itself may not be an issue, but what we were saying is that there were, in many instances, what happens is that these signals are used as part of control systems, and the control systems do something called proportional, integral, or derivative control. And I had the acronym there. Let me see if I could get my stylus back up here. Hold on. Yeah, just a second. Right, I was trying to get the stylus working. That we had PID control, and the PID control basically was proportional, integral, or derivative. For some strange reason, I'm not getting my stylus functioning here right now. I'll sort that out in a while. And because of that, you have that this signal, let me go backwards here a little bit. So if this was a signal, what happens is that the signal itself now, when it goes through a proportional, well, that's easy, that's amplification or derivation, but integration or derivatives, right? That the signal itself, what happens is that the integral or the derivative of the signal changes what happens to the actual signal coming in, and now the system has to respond to something totally different. In our earlier discussions, we had said that if you take a step and you integrated a step, right, there are two sets of things. If you integrated a step, you got an impulse. If you took the derivative of a, sorry, if you integrated a step, you got a ramp. If you took the derivative of a step, you got an impulse. So all of a sudden, you have these sort of different signals that the system has to cope with, right? And we will see the effect of that a little bit later on too in some other discussions that we're going to have. Okay, so just what I want to do today is to finalize that discussion we are done an intuitive look at it, which is what I have on the screen here. And we will finalize that discussion today in this class. But give me a second and let me find out why my stylus isn't working so I could kind of mark here on the screen a bit. 2 seconds. Right, okay, so there we go. So what we said last time is that if you had this just intuitively, that this bit here would give you some dxt dt. This one would give me, at this point, the signal is here, so you'll have your dx dt here. But here is where the issue came up. And what we saw is that if this, I'm assuming that this sort of, we were taking a derivative of this signal, we have a sudden change here that this signal at some point in time is this value, which is x at t1, and then an infinite time later, it changes to another value here, right? Also at t1, but it's like x1, x1 at t1, and it's now changing to this value here, which is x2 at t1 also. That we saw was a step change. So what you had was x1 t1, which is just before this sudden discontinuity occurred, and then afterwards we had a value here which was x2 at t1. So there was a step change. And if I were to take the derivative of that, we saw that the derivative of the unit step from a previous slide, the derivative of that was the impulse. So what something like this would do, notice that this is a step. It is a negative going step. So it's going from some value to a lesser value. So if I were to take the derivative of that, what I'm going to land up with, the derivative of this is going to give me an impulse. And the impulse, the size of the impulse is the difference in amplitude between x1 at t1 and x2 at t1, right? And how we drew that, we said, is that at this point, what I would do is to draw an impulse, a negative going impulse, and the weight of the impulse here is that distance, whatever is the difference between x at t1, x2 t1, and x2 at also at t1. Excuse me a second. Oops, yeah, little office call there. All right, and we saw that we did some of this last week. So let's look now at something just like this. So here now you have, which is typical of the kind of situations we'll discuss and the sort of questions that I'll ask you about. Here you have the same sort of arrangement, but look very carefully at what we have here. We have 3 points of discontinuity here. We have T1, right? We have the T1 point. We have a discontinuity at T2, and we have a discontinuity at T3. So if I was to ask you, what is the derivative of this? As I said, intuitively now, I need you to be able to understand what to do here. Okay, and it's fairly straightforward. If you look at this, the signal, you have nothing before here. And then at this point in time, it changes to a value here. Okay, so we have a step change at T1. Then X1 behaves itself nicely all the way through until here. At this point, we have a step change from this value here, which is what we had before. So this will be X1 at T2. And then here is going to X2 at T2. So there's a step change here, right? Then X2 is whatever the signal has become. And then at this point in time now, it changes from this value here, which will be X2 at T3, right? It changes from this value and it goes to 0, right? So if I were to take that, and of course, if you're not following, let me know very quickly. So what is the derivative of this? We have to recall, let me get a different color here. So we have a step change here. This is a positive or negative going step. Quick question, positive or negative going step? Plus it'll let me know if the audio is working. Anyone? Anyone who had their coffee?
Positive.
Yeah, that was seriously sleepy. Anyway, so we have a positive going step. So what's the derivative of a positive going step? The derivative of a positive going step is an impulse, a positive going impulse. And as he said, the impulse starts at the axis here and it's going up. The height of the impulse is this height here, which is x1 at t1, right? So that's the height of the impulse. dx1 dt will be something. So if you have to just sketch this, just sketch something, you know, dx1 dt, we don't know what that's doing. So this is dx1 dt, draw something. dx1 of t dt. Here now, we have a step change, and it's going from this value to a lower value. So this is going to be, which is what we discussed before, this is a negative going step. So how we draw that, again, is an impulse. The derivative of that is going to be a negative going impulse. And the height of the impulse, or the weight, I should say, of the impulse is x1 t2 minus x2 t2, right? This is what we discussed last time. Here now, inside of here, x2 does something. So this, you just draw something. This would be dx2 dt. And then finally here now, at this point in time, it's going to change from x2 at t3 to nothing. So this again too is a negative going step. So the derivative here is going to be a negative going impulse. And the weight of the impulse is x2 t3, or the difference between this point here and that point here. Okay? And of course, the derivative here is 0, the derivative before is 0. All right? So the answer to this, to sketch the derivative, this thing will have 3 impulses now, which is 1 positive and 2 negative going impulses. Every time there's a sudden change in it, you would get an impulse. And in between you have, well, whatever dx1t and dx2t looks like, dt. Right? We don't know they're continuous, so they have some function that represents the function itself. Yeah? Make sense? Everybody following?
Yes, sir.
Right. So this is just a maths here for it. Okay? And this is the answer, of course. And what we have done here is now to position, is to actually put the impulses. If you have to label it now, if this is 0, this is occurring before the 0 at t1. So this will be the delta at t minus t1. And the height would be what we had said before, it should be x1 at t1. Here, the impulse is after time 0, so that is at t minus t2. Here is t3, so the impulse is at t minus t3. Okay? So the complete drawing, if you were asked, and you would see some past paper questions on problem set questions like that. If I ask you to draw a labeled diagram of the derivative of that piecewise continuous signal, this is what the answer I would expect to be. To show each impulse, all right, to show where the impulse occurred, to show, well, an estimate, any kind of shape of what the derivative of the continuous time signal was, okay? And to give me also the value, it's not here because we did it on the previous slide, what is the weighting of the impulse plus the impulse weight, right? Meaning size, right? Size or length, however you want to put it. And the important thing, of course, is that all the impulses start on the origin. As I told you also, sometimes people forget, and in the course of the exam or answering something, that you put the impulse here. All right. So if that is there, what you would lose is like a half mark or something for that, because I recognize that you know what you're talking about, but you drew it kind of floating in the middle of the year. So try not to get that happening. Okay, that is 3/4 of the answer there. Fair enough. Yeah.
Yes, sir.
Okay, and then just one little comment on something here. If this, which is like a square wave or something, if you were to find the derivative, you would have passed this through something that is taking derivatives all the time, then what you're going to create from this are a series of impulses. So the derivative of this is 0. This is a positive going step here. So this is going to give me a positive going impulse. Here is flat, so the derivative of that is 0. This is a negative step, so you're going to get this nothing impulse, right? Nothing impulse. So this kind of thing, if you have any system that is working on a signal like this, and the signal itself, for some reason, you inadvertently pass this through a derivative piece of control or something, and as I said, you'll meet that in time to come. You're going to unfortunately generate a series of impulses. And you remember what impulses are. Impulses mean that whatever it is going to try to go to its maximum value in a limited period of time. Okay, so if this is a motor, then the motor is going to suddenly accelerate to its, or try to accelerate to its maximum speed. And then a very short time later, you get an impulse trying to stop the motor by giving it a reverse voltage in the opposite direction. So that's the kind of the consequence of having to deal with piecewise continuous signals. And as an engineer, one of the things you will meet here, and as I said, in your career as you're going along, you will meet, is that you always have to design for the worst case. Always try to anticipate what is the worst thing that can happen and cater for it. All right. So any questions on this? Because before we have a look now and see what a step response and an impulse response in something real, a real circuit, what it actually looks like. Okay. Nice. Of course, always feel free at any point in time, you can ask me for ask questions and so on. All right. So let me share now the other one. Where are we? Good. Right. So to continue our discussions now, we've seen that in sort of review of what we've done. We spoke about signals and systems in general. We said now that because of the huge variety of signals that systems have to cater for, it's not practical to test up any system with that number. So we have a set of sort of standard signals that we use all the time. And if we figure out the response to that, we're fairly certain how the system will respond to everything else. And the step response, the step signal was 1, the impulse was 1, the sinusoid was 1, and the ramp was the other. So let's have a look now at a little more in depth into what a step and an impulse response causes. Okay. So in perspective, again, what is the purpose of doing this? By now, again, you're asking yourself that at 8 o'clock on a Monday morning, right? As I saying, the whole thing is that we are doing applied science, right? Engineers supposed to take what the natural scientists and the mathematicians do And we are supposed to be able, that's the thing about us, which is why we tend to expose you to a fair amount of mathematics as well. You need to understand when scientists come up with something, how to apply it to the real world, right? Science is good, but if it has to have some purpose behind it. And this is where engineering comes in. So we want to take the developments that scientists make and make something useful out of it to benefit mankind and humanity and to make things better for us. Part of doing that is to design systems. And the thing about designing systems is that you have some sort of requirements that you're looking to solve. It could be flooding in an environment, so you want to make something to detect water rising in the road or rising in a residential area or rising in a river. Right now we're dealing with a lot of global warming, so weather patterns have changed. So you have some system that you want to design, and it has certain requirements. There's always important. There are always some requirements that somebody is going to give you. Next year, please God, when you do your ECNG2011 project, you're going to see very carefully or very clearly what the requirements for a project are. And even now, you could probably go onto the 3020 site and see when someone puts up a project, which is an engineering design of some sort, that there are requirements. In other words, there are some sort of things that the thing has to be able to do at the end. Okay. So once you make the thing now, so you have something and you have designed a system, right? This is the system here to meet these requirements. What you have to do now is to figure out how this system is likely to respond to all of the signals coming into it. That is impractical. So what we do is to substitute for every signal in the world, we substitute a certain number, a certain set of signals that we will use. Okay, and if it works for those, then we are fairly confident that it's going to work for all the real world signals that are there. And the signals, of course, are the step, the impulse, right, and the sinusoid, and to a lesser extent, the ramp. Okay. And what is known usually about any problem that you are asked to solve, you know a couple of things. You know the absolute limits of the output. So you know, for instance, what is the power supply. So if you're working with a microcontroller, you know that the absolute output limit for the microcontroller is going to be 5 volts. Right? Or some of the smaller low powered ones might be 3. The maximum output you're going to get is 3.3 volts. If you're going to interface or connect that to the utility outside, right? The normal thing you have is 120 volts AC. You may have 240 volts AC. And then, of course, if that now in turn connects to you working in a utility generation place, then this, of course, is going to go up into the high voltage range, right? Kilovolts, as the case may be. If you're working in renewable energies and so on, then you're probably going up. I should put AC here, right? AC. If you're working in renewables, for solar, this could go up. You could be dealing with several hundred volts DC. And similarly, if you're dealing with wind power and so on, you could have several hundred volts AC. You also will know the signal frequency. Okay, the signal frequencies are the kind of things that the circuit will be expected to deal with. So if it's audio, you know you're dealing with something like 20 to 20 kilohertz. Okay, if it's power generation, you're dealing with 60 hertz or maybe 50 hertz, depending on where you are. All right, things like that. If you're dealing, if you're into the communication field, you're going to be up into the gigahertz, into the high gigahertz range. And so you go on. So you know a number of things, right? The absolute output limits. you typically know what sort of speed of response is required. So if you make a change, how long should the thing take to respond? Okay, if it is a car, when you turn the steering wheel, you want the direction to change instantly. If it's an aircraft, same sort of thing. If it's something like we mentioned last week, like an incubator for premature babies, if there's a temperature change, you want the incubator to respond very, very slowly. Okay, so all sorts of things. And then the range of responses. So there's a span of acceptable values. So like we said, for the AC, in the AC power generation, you have about, you have 6%. Okay, in many cases, depending on what you're dealing with, there is a span. So if the output has to go to something, there's always a plus or minus value that is acceptable. We saw a brief introduction to that in our current discussions on power supplies in the other class. Those of you who are doing the other class, when you're designing a power supply, you have an output voltage, but there's a ripple, right? There's a ripple, which is a plus or minus voltage on the output. Okay, so all of those things, you know that. All right, you can't design something unless you know something about what is the situation that you're going to meet. And then what you have to do, again, what is possible is to determine the range of possible input values, again, for frequency and amplitude. What you will not know is what sort of shape the input will take. So for instance, if you're dealing with an audio amplifier, you can know that the output is going to be, let's say, 10 volts. Right, so it's going to be plus or minus 10 volts. You know that the frequency is 20 to 20 kilohertz. Right? This is going to a loudspeaker, so you know that the impedance of the loudspeaker is, let's say, 16 ohms. Right? What sort of input value here you're dealing with? If this is 10 volts, and you know that the gain of this is, let's say, 10, so the maximum input is 1. Right? You know these kind of things. What you don't know is an audio signal is all over the place. Right? So you can't really always check it like that. So what we do is to substitute our test signals here. And as we go through this, we will see that what we do with these test signals is usually more than enough to figure out what the thing is going to do later on. Right? And what you conclude is, depending on how the response to the standard signal is, you could say with fair confidence how it's going to work in the real world. And more often than not, in our engineering world, there are two typical tests that we conduct on systems early on. One is a step response, and one is an impulse response. And these particular signals test the system very rigorously. And if you know how it, and because of that, it really, when you do a step response or an impulse response on a system, that is a point when the system will fail. And when it fails, you could see what caused the failure, and then you could go forward from that point. Right? So let's look at, for instance, if I have a simple thing, here is a simple RC circuit that you met in physics. And you ask something now, so we're doing a step response. So here you have a DC supply, you have a simple resistor and capacitor, and you're looking now, you're monitoring the voltage at this. This, you assume that the capacitor has 0. We have a DC source here, and we switch the circuit on. And we said last time that when you switch the circuit on, that is the equivalent of putting a unit step onto the system. So you switch that, what happens to the voltage across here? And if you remember, again, this is more revision and so on. You remember that the input-output equation for a simple RC circuit is a differential equation, because there's a rate of change. The voltage across the capacitor it depends on sorry, the current through the capacitor depends on the rate of change of voltage and so on. So you have this is the description. So this is how that circuit works, which is all fine and good. But I want this. I just want YT. Right? So telling me this is part of the answer, but it's not giving me, if I give you this, it's not giving me a whole set of information. What you want to do is to solve YT. And how we solve it is these differential equations. Of course, you could integrate and do it, but we learned a technique called the Laplace transform, which we will start reviewing in a short while. And if you apply the Laplace transform to the equation, and you assume that the capacitor didn't have any voltage on it to start with, you get an equation looking like this. Right? This is in the Laplace transform domain. So you have gone from our sort of universe into somewhere else. Right? It's now a function. Instead of a function of t, it's now a function of this variable that we have decided, that was decided many years ago, that we will call S. Okay, so this is the input, output. This is the input here. This is the output, the Laplace transform of the output. This is the Laplace transform of the input. And this is what this system does. Right, so this is the Laplace transform of the system. Right, meaning this RC network here. So the system comprises this. Right, so that behavior is described by this piece of mathematics here in the Laplace transform. So we have this, and we want to know, okay, we have a step. We just said that when you switch it on, xt is a unit step. We have the system expressed in terms of the Laplace transform. So xs, if we recall, is 1 over s. All right, we will do a brief revision of that in a couple of lectures, but if you have, you should be able to recall it now. I know it's a year since you did it, but you should be able to pick up something from this. In fact, it's less than a year, I think. ECNG2011 would have been a semester 2 course, if I'm not mistaken. So you now have this here. So this is xs. So we have ys now in terms of all of this. And what is YT? Well, you do some manipulation and so on, and we'll review all of that. You do your partial fractions and so on. But eventually, if you don't make any mistakes, you come back to the real world, and this is what YT looks like. Remember, YT is the voltage on the capacitor. The RC here. All right. I've put a step change here on it. This is a DC source, and I'm looking at the voltage across this capacitor here, which is YT. Okay, so this is the behavior of it once t is greater than naught, because we have a unit step. So we start in the unit step here, t equal to naught. So the capacitor is discharged. So YT is 0. So what does YT look like? Well, if you plot this and you assume some values of R and C, you get something looking like this, which is kind of expected. So I have put the input, which is, let me get a different color. Yeah, that's good. So the input is a unit step, which is this. The input is a red line, and the output, which is the voltage across the capacitor, is this, that blue line across here. So this is what the step response of the RC circuit looks like. So we've done a test, we put a step on it. This is what the step response looks like. And as you can see, the step response now has a couple of parts to it. There's a part where the value of the voltage or the output of the capacitor, remember, it's this again. Right, so we're looking at the voltage here. Right, so once I put this step voltage in here, for a while, depending on the value of R and C, the voltage, of course, this is a sudden change. Remember, step voltage is a sudden change. It's going from 0 to 1 in 0 time. It's a real system, so this capacitor cannot respond, so it takes time. So it takes its time and it goes from 0 here. And eventually, after some time, it has achieved the 1 volt value of the step. This part here is what we call the transient time. And the space inside of here is a transient response. Transient means changing. So when you put a step response on the system, it takes a little while to change. And that period of time is what we call the transient response time. And then after that now, it settles to the value and doesn't change. And this is a steady state response. So you put a step onto the system, and the response of the system is a two-part response, a changing part, which is what we call the transient response part, and the steady state response part. So this is giving us some information here already. We can see first off that, of course, if the input is that the output does not respond suddenly, the output takes some time to respond. Secondly, we can see clearly that the output is steadying here, but it doesn't do anything funny. So if after the step response, notice that it doesn't go up and up and up and then come down, and we're going to see things that will do that kind of behavior. And eventually it's settling down to a steady state value, which is equal to the input voltage, which is 1 volt in this case. All right? So by testing the system with a step already, we could get some idea of the behavior of it, and we can verify that the system is at least not behaving unexpectedly. What do you want to ask a question? All right. What about the impulse response? So if the impulse response is xt, sorry, is delta t, xs, if you remember that, xs for an impulse is 1. Right? We have the proof here because if the Laplace transform, and we'll go through this again when we review the Laplace transform just for completeness. Remember, the Laplace transform is the integral between 0 minus of the signal xt e to the minus st dt. But you remember, this bit here is the definition of the impulse, and because the impulse is delta t, which is at t equal to 0, it sifts out the value of the function here at t equal to 0. And the value of this, if I put a 0 inside a e to the naught, is 1. So xs is 1. Right? Remember, we spoke about that last time. So it sifts out the value. So xs is 1. So the impulse response in the Laplace domain is ys. And in the time domain, again, if you find the inverse Laplace transform, you get something, an equation in time looking like this. What does that look like? This is what the response, remember, it's an RC circuit again. Right, this is yt here. And what we've done is to put an impulse in here. What is an impulse? An impulse here, a unit impulse, is something, a very sudden change. The weight is 1. So what this is asking the system to do is to change just at time 0. You get a sudden change at time 0. How does the system respond? Well, look at what it does. For this particular thing, where RC is 10, the weight of the impulse is 1. The system kind of gets up to about 1/10 of that. So the capacitor, because of the RC, it obviously can't respond to the impulse, but it responds a little bit. So it gets up to about 0.1 volt. And then by that time, the impulse is gone. Remember, the impulse is 0 time. The impulse is gone, and then the capacitor, of course, just simply discharges itself again. All right. This kind of thing, depending on what you're dealing with, when you put an impulse, you would get the system. So you put the impulse here. Sometimes the system will not respond. Sometimes it will go immediately to VCC and stop, fuses blown, etc. Other times it will get to a fraction and then settle down again and switch itself back off. This is a good response. Nothing has blown, right? What could have happened is that this could have just gone and then the power supply or the fuse blew. Yeah, if you make R and C too small, that may very well happen, right? So for instance, remember this is where when you turn the sudden voltage on, this is charging the capacitor. So if you make this too small, the capacitor, the current charging the capacitor will be too big and you can burn the capacitor or blow it, all right? So that is the purpose of this kind of testing, to put, this is a simple RC circuit, of course, but by imposing an impulse on it, what you've done is just kind of see, wait a minute, is it going to respond or is it going to over respond, try to respond too fast? And in some cases, the thing just burns, all right? So questions. And we're going to meet this in a number of ways as we go forward, all right? So understand it conceptually, but as we go through the question of impulse response, step response, we're going to look at very, very formally a little bit later on too, because there are some strange behaviors that happen, especially to other types of systems, as you put a step and you put an impulse response on it. Questions? And just for our purposes, we have the system equation here. All right, where am I? Let me just go back here. So we said that this bit here, right? This was the system, right? When XS is 1, in other words, XT is an impulse. When you get this, just let me go forward a little bit. When I get this now, remember at this point in time, XT is delta T, so that XS is equal to 1. What we have here now, right, is something called a transfer function. Right? And the transfer function is the Laplace transform of the impulse response of a system. Right? So from now on, whenever you hear, and you're going to meet that term transfer function all over the place, now and in the future, whenever you hear somebody talking about the transfer function of a system, what they're talking about is the Laplace transform of the impulse response of that system. Yeah? Fair enough? So questions? None? All right. Not a problem. As I said, you have the questions. Tomorrow you're going to meet face to face, of course. So if there are any things that need clarifying, it's easy to do it at that point as well. Okay. But look over what we did. As soon as the recording is available, I'll put the link up for it. I'll put it on so you could replay what it is and understand what we were talking about. All right. Okay. So I'm going to end the recording now.